Hello student, hope everybody is fine. Today I will give you some sets of lectures on the internet. Today our lecture is about second order differential equations with constant coefficients. Okay, so this kind of ordinary differential equation, it is in the form a y double prime plus b y prime plus c y is equal to a function q of t. This is the general form. A, b, and c are constants. Okay? Before I start to solve these types of equations, I would like to mention that where you will see these types of equations in the real life or in engineering practice. Okay? I'm looking, of course, for the solution for this equation. I'm looking for the function y. Y is a function of time, usually. What is the function y? To solve these types of equations, I will give you an example from practice that engineers usually need to solve. Suppose that I have a high-rise building. This is my building with several stories, maybe 7, 8, okay, or more. And this type of structure is exposed to a dynamic loads during its life, such as a wind or earthquake excitation. So engineers usually want to design their structures to withstand this lateral loads, and they need to find what is the maximum motion of the top of the building. What is the value of the top of the building, the motion, the displacement at the top of the building. So you may make a very simple model to check your computer analysis results. Usually you will use numerical methods to solve these types of problems using some softwares, but to have an engineering background, you have to check your analysis results. So you may simplify this problem as modeling all the total mass of the structure as a one mass, lump mass. We call it the effective mass. And all the stiffness of these columns and beams as a one effective stiffness K. And during base ground excitation, what will be the lateral motion y? So if you apply the Newton's second law for this, summation of all the forces act on the structure is equal to the mass times the acceleration. Okay? You can write this equation as follows. This is actually nothing but it is just can idealize it as mass splitting, as you study in physics course. This is the stiffness, this is the damping of the structure, and this is the mass. And if it is excited by a ground motion, you can write the Newton law for this, and you will obtain the following equation: m y double prime plus c y prime plus ky is equal to minus m g or y g ground. Okay, so as you see, we have here, this is your force, and there is two forces going back, ky, if this is motion is y, and this is a c y prime. This is the damping coefficient related to the velocity. We call it the first derivative y prime. And if you write this types of equation, you will find that it is minus ky minus the y prime c is equal to the mass times the absolute acceleration, which is the ground, the relative acceleration y double prime plus the ground acceleration y double prime g. And if you arrange this, you will obtain this equation that I obtained it here. So from here, my y is the top displacement, and my mass is a constant number. I know the mass of the structure, and this is the damping of the structure, and usually we use a constant value for this as a 5 for concrete structure, a 5% damping. And this is the stiffness of the columns, and this is also the beams. It is also a constant number. So if I can solve this equation, I will find the maximum motion, and it will stop, of course, in the case of after some time. So I'm looking for what is the maximum value for y, how many centimeters it will move, and in this case you need to solve this type of problems. Okay, so this is one of the applications that engineers need to find. Now, in general, so I have what we call, I have an engineering system, which is my building in this case, and it has a properties, it has a mass, it has a stiffness, it has a damping characteristics, and I have input action. In this case, this is the earthquake or wind action, dynamic action, and I want to find the output is my response. Response is the top displacement. I want to predict theoretically what is the motion of the building at the top place. Okay, so the second order equation, you know these characteristics m, k, and c, which is the constant here, and you know the action. You can't change the earthquake risk on the building. For every place or location, there is seismic seismic risk for each location. You can't change this, and under this action you will see the response. If you are not happy with this value, suppose that the maximum displacement is 20 centimeters, and you are not happy with this value, you want to make it 10, for example. Okay, so you can change the characteristic of the system. You can change the stiffness. For example, you may increase the thickness of the columns. You make larger columns, okay? And in this case, or you make a shear wall here, you make a wall. So in this case, the stiffness will increase, and as a result, your response will reduce, okay? So these are in your hands. These coefficients, which I call it A, B, and C, I call it in the general form. These are in your hand, A, B, and C. You can change these numbers, and you can solve it again, and you find the response. If you are happy with this response and you reduce your displacements, then your structure will become more earthquake resistance. But you can't change the action, okay? This is the goal of how we do that. You have to, this structure have to carry these types of action. Okay, Thank you for watching and see you in the next video. Thank you.